lesson is on applying the theorems that you've learned. Now, what we're going to do here on the front, you have 4 theorems that you have learned so far. And what we're going to do is I'm going to try to get you to remember them without looking back at your notes. That's going to be fun. Why don't we start backwards? Mean value theorem. Okay, so mean value theorem says that if f is continuous on the closed interval and differentiable on the open interval, then there exists some number in that open interval such that what? Not f of c, f prime of c. Remember, mean value theorem. What's mean mean? Average. Yep. You're thinking about Rolle's theorem. Remember, I rock equals a rock. We'll pick up there after lunch. We're working backwards. Rolle's theorem. Criteria on Rolle's theorem. Let's see. If f is continuous, on the closed interval, differentiable on the open interval, and what? F of a equals f of b. Then there exists a c on the open interval a to b such that f prime of c equals 0. Extreme value theorem. Remember that one? Right. Extreme value theorem. If f is continuous in the closed interval a to b, then how do I want to write this? Okay. Then f has an absolute min and an absolute max at x equals a, x equal b, or at some value on the open interval, so some value between a and b. I'd like for you to write it like this just to remind yourself it could be at the endpoints. Okay. Now, Sparks has one thing added in here, such that f prime of x is 0 or undefined. This part goes together right here. At some value a on the open interval a to b such that the derivative is 0 or undefined. I don't particularly care that you put this piece in there, the such that part. Just know that the idea is if the function is continuous on the closed interval, then there is an absolute max and there is an absolute min, period, end of discussion. Does anybody remember the intermediate value theorem? That's the, what? That's Rolle's. That's Rolle's theorem. You're on a roll. Yeah, yeah. If, Ransom, how tall are you?
6'1".
In 7th grade.
At some point you were
In 7th grade, you were, say, 5'5". Then there had to be some time between the 6th grade and 12th grade that he was 6 feet tall.
Yep.
That's the intermediate value theorem.
Yep.
So the only thing that has to be true about the intermediate value theorem is that the function must be continuous. Height is a continuous function. You do not skip heights. Okay, if f is continuous on the closed interval a to b, use k, and the value k is between f of a and f of b. Some number. In this case, Ransom's height is continuous from the 6th grade to the 12th grade, right? This value k would be between his height in the 6th grade and his height in the 12th grade, okay? So in this case, maybe it was 6 feet. If the value of 6 feet is between 5 feet 6 and 6 feet 1, then there exists a C on the open interval A to B such that f of C equals K. Just remember, that's the height one. We can draw pictures of each one of these if that would be helpful to you. Would it be helpful? Okay. Once you have this written, then we'll go back and draw some pictures. Everybody got IVT written? So IVT would say let's go year in school and height. And let's say in the 6th grade and the 12th grade, and there's 5'5" and there's 6'1". We know that height is a continuous function. So we know that if there's some height in between 5'5" and 6'1", let's just make it a little bit easier to see. Let's make it 5'9". Did Ransom ever have to be 5'9" somewhere between 6th grade and 12th grade? Has to. So if, let me put these points in here. If f is a continuous function and 5'9" is somewhere between f of 6 and f of 12, then there has to be some value c between 6 and 12 such that f of that value, that didn't work. That didn't work. Let me move it. Right there. There had to be some value between 6 and 12 such that at that time he was 5'9". That point is called C. That x value is called the C value. Yeah. Anybody need more time to draw that picture? You all right, Emily? Okay. Let's go to extreme value theorem. Now, he had a neat one drawn. Okay. And he called that D, and he called that C. This function is continuous from A to B. So from there to there, this function is continuous. So that means there has to exist a maximum, an absolute maximum, and an absolute minimum, either at an endpoint or somewhere in between the ends. And if it's between the ends, then it's where the derivative would be 0 or is undefined. Mm-hmm.
So it can't be on the end of it?
It can be at the end. It can be an endpoint. Now this is, I'm not having to take a derivative because extreme value theorem has nothing to do with the derivative.
You had like this such that the derivative of x equals 0 or undefined.
But remember, that part only applied to the open interval. That part only applied to the numbers between the endpoints. But you're right. That's not on the endpoints themselves. That piece was if the absolute min or max is on the open interval, meaning not including the endpoints, it would be where the derivative is 0 or undefined. So if you'll notice, we have an absolute minimum right there. That's where the derivative is undefined. We have an absolute maximum right there on an endpoint. Questions? Okay, let's go down to Rolle's. Rolle says if the function is both continuous and differentiable on the closed interval a to b. And he drew this. But remember, we're only looking from a to b. If the function is continuous on the closed interval a to b and differentiable on the open interval between a and b, then there exists at least one place where the derivative is equal to 0. Derivative is equal to 0 right there, and right there. Remember, the differentiable part means that there cannot be any pointy places or cusps. Okay? And then the mean value theorem. I don't know what just happened. What did he do his picture? Here's A, and here's B. The mean value theorem. Oh wait, you know what? I didn't show you on Rolle's. What was the deal on Rolle's? The ends have to be the same, have the same y value, don't they? So that end, that y value, and that y value have to be the same. So don't forget that part. Mean value theorem, remember, I rock equals A rock. Mean value theorem says if the function is both continuous on the closed interval and differentiable on the open interval, how can you look at this and say, I know this function is differentiable? It's continuous. It's not undefined anywhere. There are no pointy places, no cusps. Okay, never have to raise my pencil, and that's the continuous part. I could draw a tangent line at any point between A and B, couldn't I? Yeah, so this function is differentiable. Then the mean value theorem says there is some point between A and B where the slope of the tangent line is equal to the slope of the secant line. This one is A rock, that's the secant line. This one is I rock, that's the tangent line. Now, folks, the rest of this is just actually applying the theorems. And you got your calculators. The rate at which water flows out of a pipe in gallons per hour. This is I thought I just told it to give me a highlighter. The rate, this is a rate. Please be careful, this is a rate. Is given by a differentiable function. Oh, if a function is differentiable, then the function is continuous. The table shows the rate as measured every 3 hours for a 24-hour period. The water is flowing out of a pipe, and this is the rate in gallons per hour at any of these particular hours. Estimate the value of r prime of 5. From a table, how do we estimate a derivative? Slope of the secant line, right. Of what 2 points if I'm going to do 5? Okay, so r prime of 5 is going to be about r of 6 minus r of 3 over 6 minus 3. This is not anything. This is just something. This is not a theorem right now. We're just approximating a derivative. Point 4 over 3. If I multiplied top and bottom of that thing by 10, what would I get? 4 over 30, which is simplified to 2/15. What are the units of measure? No. What? What? Why? The rate is changing. This was in gallons per hour, and I took its derivative. So it's going to be gallons per hour per hour. Gallons per hour per hour. So you're going to say, let me just write it here. The rate at which water is flowing out of the pipe is increasing because you took the derivative of a rate. By 2/15 gallons per hour at time 5. Be careful on your units. This is like the difference, it's like taking the derivative of velocity. The derivative of velocity, which is miles per hour, is acceleration, which is miles per hour per hour. Let's go back and talk about a car. If your velocity is 55 miles an hour and you start to accelerate, okay? Let's say you're accelerating 5 miles an hour every hour. That's kind of how it. All right, using correct units of measure, find the average rate of change from hour 3 to hour 18. How are we going to do that? How do you find, this is a rock, Average rate of change. How do you find A rock?
R of 18.
R of 18 minus R of 3 over 18 minus 3. So every hour, Adam, your rate of speed would be increasing by 5 miles an hour. So hours per hour. It's hard. It's hard to get your hands around. What's this, 10.7 minus 10.4 over 15? Which would be, what'd you say, 0.3 over 15, which is 30 over 150, which is 1 over 50. What's that? The average rate at which the rate of change. Sorry, 3 over 150. Yeah, which is simplified to 1 over 50. Yeah, this is right. Did I say it wrong here? Yeah, that'd be 3 over 150, which would be 1 over 50. So, what are the units on this?
Gallons per hour. Per hour.
Gallons per hour per hour. And if you're taking the derivative of a rate, it's going to be per something else.
So like on the first one, why did I ask for the first one? So it's like when it says the average rate of change, so it's the same as the derivative.
Average rate of change is over a time period. The derivative is at a specific moment in time.
Well, like, if we did the same thing, though, fine.
No, but remember, here, when we did part A, look what part A was. Part A was an approximation. The only way we could approximate the derivative at 5 was to do the slope of a secant line because we don't know exactly what happens at 5. Because we had a table. So what we got on part A was an estimate. Okay?
So like it gave us like what it's like if 6 or like 5.
Well, see, here's the deal. The issue is, this is a table, right? If it had given us the equation for this data, we would have taken the derivative and evaluated that at 5.
So like even if it had given us 5, we still have to give the 2 points.
Because I don't know what what the rate of change of that rate would be. It's like I'm finding the acceleration.
Average change of
If it's like Maggie, if I know the velocity, I'm just trying to find the acceleration. I'm driving at 55 miles an hour, but I'm speeding up. And my speeding up would be, I'm speeding up by 5 miles an hour each hour. It is. All right, let's look at part C. Is there some time, folks, when you see any wording, give me my highlighter. When you see any wording like this,
yes.
it's asking you for a theorem. It doesn't ask you to evaluate anything. It just says, does something exist? That means theorem, 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 theorem. Now, what you've got to do is you've got to decide, all right, what theorem asks me about that? Rolle's. I bet you were asking about Rolle's theorem. Well, right. What are the conditions for Rolle's theorem? So, I've got to see if that applies. Is the function continuous?
Yes.
How do you know that?
Because the rate is to the differential.
Because dadgummit, it said the function was differentiable. So, from 0 to 24. Notice, went right by it. Went right by it. 0 to 24. Okay? F is continuous on 0 to 24. Right. Because the definition of Rolle says continuity on the closed interval. Right? F is differentiable on the open interval. Now, I want you to notice, remember the last piece of Rolle says f of a has to equal f of b. Now, is there some time in this interval here where the derivative is 0? Does that last piece, is that last piece true anywhere? On that interval, is f of a equal to f of b anywhere? Yes. Where? 0. F of 0 equals f of 24. Therefore, Rolle's applies, which means there exists a C on the open interval 0 to 24 such that f prime of C equals 0. Go ahead. Yep. You write it like this. They'll probably call that a spelling error and not worry about it. A spelling error they're not going to worry about. It's like if you put this and it should have, if you put this and it should have been this, that's a spelling error. No big deal. Now, I make it a big deal in here. But they will have a few things that they're just not going to, in the big picture, that's not an issue. Next page. Business. I wish they'd use something else. I don't like Pepsi, but okay. I like Coca-Cola. I don't like Pepsi. No, they don't. You think they do? Well, I don't think they do. Okay. The total order and transportation cost C of X measured in dollars of bottles of Pepsi is approximated by that function. This function is the total order and transportation cost, where X is the order size in hundreds. X is the, come on. What's the matter? You just want to rest? What's going on? It's a sign. Yeah. Oh. The number of bottles in hundreds. Answer the following questions. Is there a guaranteed value of R on the closed interval 0 to 3 such that the average rate of change of cost is equal to C prime of R? Which one? Why is it the mean value theorem? Because it's asking when is the average rate of change equal to the instantaneous rate of change. When is IROC equal to AROC? Yep. So the question is, does the mean value theorem apply? What are the criteria for mean value theorem? Doesn't tell us continuous. Is this function continuous on the closed interval 0 to 3?
Not 0.
Now, the function's not continuous at 0, is it?
No.
So, does mean value theorem apply?
No.
No. So you're going to say, since C of 0 is undefined, MVT does not apply. Now, what does that mean? There is good. There is no guaranteed value on the closed interval 0 to 3 such that IROC equals AROC. It might be there, but it's darn sure not guaranteed by the mean value theorem. Yeah. Is there a value of R on the closed interval 3 to 6 such that C prime of R equals 0?
Yes.
What theorem? Look, is there a value? Folks, yeah, please. Come on, highlighter. Work with me here. I'm not asking for much. Okay. And you say, is there guaranteed? Is there a value? Theorem. On the closed interval 3 to 6 such that C prime of R equals 0. What theorem am I thinking about? Why Rolle's? I want to know when is the derivative equal to 0. Is this function continuous on the closed interval 3 to 6? Where is this function discontinuous? -3 and 0. Yep. Which are not on that darned interval, right? So, what was it? C? C of x is continuous on 3 to 6. What else for Rolles? Is that function differentiable on 3 to 6? Well, I don't know. I guess we better figure that out, eh? Now, look, if I'm going to take the derivative of that bad boy, I'm going to rewrite it. I'm going to show you how I'm going to rewrite it. I'm going to rewrite it as, not that way. C of x equals 10,000 over x plus, what is it? X over x plus, do I want to do it that way? No. Change my mind. 10,000 times 1 over x plus x over x plus 3, is that right? You could distribute, or you could use, look, that 10,000 is just a constant, isn't it? It's just a coefficient. So we can just pull it out and not worry about it and multiply it by the derivative of the inside.
Yeah.
So C prime is 10,000 times, let's think about 1 over x. Now I could do the quotient rule here and it would be fine. But if I rewrote this as 1x to the -1, isn't 1 over x the same as x to the -1? What's the derivative of that? -1 over x squared, because it's -1x to the -2. Now this part, I think we're going to have to do the, if I rewrote it as x to the -1, 1 over x is the same as x to the -1. Do you buy that this and this are the same thing? The derivative would be -1 x to the -2. All right, so let's run it. Derivative of the top, 1 times the bottom, minus the derivative of the bottom times the top, over the bottom squared. Now, yes, I know I could clean up the top. Where is this derivative undefined? 0 and negative 3. Is that on the interval I'm looking for? No. So I know this function is differentiable. C of x is differentiable on the open interval 3 to 6. Go ahead.
Can you not just tell from like that take the derivative? Like, because you got the same number.
I could have. I'm doing that for your benefit, but could I have? Yes. And if you can look at that and think the same thing, it's fine. Here's what Wendy was asking. Could you kind of explain what you were asking, Wendy?
Well, we got the same answers, but can you just like look at that and say like at 0 and negative?
The answer is yes, because x and x plus 3 are going to be in the denominator of your derivative. So the answer is yes. I just went through it for you to see it. We're thinking if Rolle's applies. Do I have any more criteria for Rolle's? Okay. What's C of 3 and C of 6? You dang right you can use your calculator. 8,000, say again? And then tell me what C of 6 is. Same thing. Woohoo! So I'm going to rewrite it like this. So Rolle's applies. Did it ask us to find it? Then we got to find it. Okay. All right. So here's what we know. So C prime of R has to equal 0, right? Well, I did the derivative. Put that in your calculator in Y1. Find the zeros. But remember, you're only looking between 3 and 6.
And then we put x equals 1. Whatever.
X is approximately what? 4 point what? All right, so all I'm saying here is that you have to evaluate the function at those 3 points, okay? The function, not the derivative. So when you get that number, you're going to say the greatest cost is whatever. Now, Sparks says it's $8,611.11. Okay, so Nikita got it, so we're good. I don't know for which one. That would be for, I think for 9. I think for C of 9. Now listen. We have 2 more. We're not going to get through 2 more. The third one, I think it would be better for us to do the 4th one. I think you can handle the 3rd one by looking at Sparks's notes. I would like for us to go to the 4th one, the table. The problem is we're taking more time before lunch going over homework. So we may have to pare that down a little bit and go over homework during Encore before school if you're needing help there. Because I'm a little concerned but you guys seem to be doing okay though. Okay. The functions f and g are differentiable for all real numbers, and g is strictly increasing. Now I want you to pay attention to strictly increasing. Come on, highlighter, work with me here. What? It has killed us some time. What does it mean if a function is increasing all the time? What do we know? Well, there you go. Rolls won't apply, that's for sure. What do I know about the derivative? So, you might want to keep that in the back of your mind. That tells me that the derivative is always positive. And as Mason said, Rolls is not going to apply. There's no way. The table above, bless you, gives values of the functions and their first derivatives that select values of x. Now look what the function h is. H, aha, that's what h is. Find the equation of the tangent line drawn to the graph of h when x is 3. What do we need to know? Sot pot. By golly, you guys know that. Sot pot. What's the x value of the point of tangency? 3. Can I find the y value of the point of tangency? How? Yeah, what's h of 3? G of 3 of f of that. All right. G of 3 is 4. F of 4 is -1. And -1 minus 6 is -7. Okay, so that's my point of tangency. What's the slope of the tangent line? Let's find the derivative of h. Oh my goodness. It's a peanut. It's a peanut M&M. F prime of g of x, the derivative of the outside. Eat the candy off the outside. And that's it. Good. So now I need h prime of 3, which is f prime of g of 3 times g prime of 3. G of 3, 3 times. Good, I got 6 too. 6. Equation of your tangent line, y minus y1 equals m times x minus x1. Thank you. Implying that the rest of my 3s are really ugly, right? No, it's okay. Find the rate of change of h for the interval 1 to 3. What's that asking?
A-rock.
Which one? A-rock or I-rock?
A-rock.
A-rock. So I need h of 3 minus h of 1 over 3 minus 1. I already know h of 3, don't I? H of 3 is -7. H of 1, well, I don't know, what's h of 1?
3.
G of 1 is 2. F of 2 is 9 minus 6 is 3. That's it. That's the average rate of change for that interval.
A-rock is the slope.
Yes, A-rock is what we just found. Average rate of change. Instantaneous means right now. It means I can figure out your speed the instant your tires hit the Illinois River Bridge on Highway 412. Next time you drive it, look. Okay. Explain why there must be, hey, pay attention, self. Explain why there must be. Theorem. Why there must be a value of r between 1 and 3 such that h of r equals -2.
Intermediate value.
Why intermediate value theorem? Because between 1 and 3, I want to know, is there a point between 1 and 3 that has a y value of -2? How do I figure that out?
Max.
Look at your front page. Okay, is this function continuous? We were told it was, right? We were told differentiable. So whatever that function was, some h. H is continuous because f and g are continuous. What's h of 1 and what's h of 3? We got those two already, didn't we? H of 1 is 3 and h of 3 is h of 3. You buy that? So since the function is continuous and this y value is between the y values of the endpoints by IVT, right, there exists a value, let me just put there exists a C on the open interval 1 to 3 such that f h prime of C equals, no, that's not right. Not h prime. I'm so used to writing prime. Explain why there is. Theorem. Is this IVT also? Such that the derivative is -5. That's not intermediate value theorem. This one's a little, it's implied. Now, I'm going to show you something. Yeah. What is this is an I rock, correct? Let's find A rock. Let's find the average rate of change between 1 and 3.
We did that already.
What was that?
Negative 5.
Oh my gosh.
A rock equals I rock.
Ah. So here's what you're going to say. The function is continuous and differentiable, so the mean value theorem applies, which means there has to be some value between 1 and 3 so that A rock equals I rock. Get it off Sparks' notes. Just get it off his notes.